Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everybody. This is my pleasure to introduce Felix Lin from Rice University. He works with Professor Lin Zhong. His research is in the area of mobile and wearable systems. Especially he tries to develop low-level software to exploit the emerging features of those devices. And for his work, he recently got the best paper award at S+. And today in his talk, he will talk about that recent work and a few other works that he did in his PhD. With that,
okay.
Felix.
Okay, thank you, Suman. Hi. So have you guys ever wondered if we can span one mobile system over highly different processors for both performance and power efficiency? So in my work, I will redesign system software to make this happen. Now let's start from why we should do this. Power efficiency rules. It has become the major concern for many, many systems, from sensors all the way to big servers. For example, in many cases, if we have better power efficiency, we'll naturally get better performance because we can switch more transistors at the same time. For mobile people, power efficiency means usability because the device itself will become cooler and will last longer. For server people, higher power efficiency means millions of dollars saved from utility bills. So that's why everybody tries to improve power efficiency. So in this race, mobile is one of the pioneers. Reasons are pretty much clear. Because mobile devices usually have very tight thermal budget. We cannot put a fan on the back of our smartphone, and also have a very tight battery budget because of small form factor. The bad thing is the two budgets do not scale up over time. There is no Moore's law for them. So let's see one example. From 2008 to 2013, we see the performance of a commodity smartphone has scaled by 20 times. But the battery capacity only scaled by 2 times. And the form factor almost does not change. So this trend is even worse. The scaling is like the other way for wearable devices. For example, Google Glass. Compared to a smartphone in 2008, the performance scaled by 4x. The battery is halved, and the form factor is even smaller. If we don't design wearable in an elegant way, things can be very ugly. So let me tell you one true story. So in our lab, we did this experiment. We run video chat, Google Hangout, on Google Glass. After 20 minutes, the surface temperature of Google Glass is 53 centigrade, which is above the human tissue damage threshold. Right? So that's something it's not quite wearable. Now, this is a pressure for high power efficiency for mobile device from the hardware side. How about the software side? One defining characteristic of mobile is a wide range of workloads, from the background always-on intelligence, all the way to the intensive multimedia workloads. And in the coming years, we are going to see this range grow. For example, for natural interface and perception workloads. So across the whole spectrum, there is 1,000x difference in performance demand. Note that all these workloads are hosted by one mobile device, and many of the workloads actually are in the same application. Ideally, the mobile device should provide power consumption proportional to performance demand. So for example, for the most intensive workloads, we want to keep the power consumption of mobile device below 10 watt, so device does not have to burn our hand. Now for the background always-on tasks, we want to keep the power consumption below 10 milliwatt, so they can still always run in the background. They can serve us.
How do you get those numbers?
From the literature. So there is a white paper, architecture community white paper. So they, like for 21st century computer architecture research, so they have these numbers, like the long-term goals.
Is it not good to have 1 milliwatt instead of 10 milliwatts?
That's an even more ambitious goal. Definitely, we should target that. Yeah. So the thing is, how can one mobile device provide 1,000x power difference? Right? So that's the problem. Now, today, a recognized approach to achieve 1,000x power difference is hardware heterogeneity. So the idea is quite intuitive. Instead of having one unified processor for all kinds of workloads, we should have different hardware for different workloads. So ideally, we can map different workloads to different hardware. We can meet the performance demand and also have the best power efficiency. So, however, in today's smartphone, because we have to achieve 1,000x power difference, so the asymmetry or the heterogeneity among those processors have to be so high. This usually gives us no global hardware cache coherence among those processors. Now, let me explain why. Let's look at the trade-off between power and performance here. Yes, Ed.
We've had this for a while, right, with ASICs. So even the earliest iPods had a CPU, but they also had an ASIC for playing MP3s.
Yeah.
So it's just that the heterogeneity was a set of single-purpose ASIC cores that did one thing, and you didn't need cache coherence because you just pointed at a stream of data and let it process, right?
Yeah.
So can you talk a little about that world versus the world you're talking about?
Right. So
1,000x difference existed there as well.
Right. So I think there are two dimensions. One dimension is the asymmetry. Right. You have very different general-purpose processors. The other dimension you talk about is the specialization. Basically, you have a CPU, GPU, and ASICs. I think we can explore on those two dimensions. General purpose is easier for application programmers to program. Okay. So let's look at the trade-off between power and performance. Let's assume we have one mobile device, and there is only one core in this device. If we want to reduce the power consumption for some light workloads, we can do DVFS. So this is a classic technique, basically to reduce the clock rate and save some power. Now, if we want to further reduce power consumption for some even lighter workloads, we can incorporate another weaker core in the same coherence domain. So this is the case for ARM big little. This will give us another 10x power saving. But if we want to further reduce the power consumption for some light background, always on intelligence, we have to have another even weaker core in a separate coherence domain. So you may have questions. Why do we have to have separate coherence domains? There are many reasons. Now, there are top 3 reasons. Number one, hardware cache coherence is complicated to design. So I talked to many hardware architects. It's complicated to design. By removing the global hardware cache coherence, it's easier for hardware designers to incorporate multiple asymmetric cores in one mobile system.
Are you suggesting no coherence but still having a shared address space, or separate address spaces and no coherence?
So at the lowest level, so there are multiple ways to integrate multiple coherence domains, right? So there could be shared memory, there could be non-shared memory. So from a software perspective, there could be shared memory address space. There could be like separate memory address space. I will talk about that later. Right. So number one, so it's easier to incorporate asymmetric cores for hardware designers. Number two, by removing global hardware cache coherence, so cores are loosely coupled. It's easier for hardware designers to design finer grain power domains. So those power domains could be independently turned on and off at runtime to save power more aggressively. Number three, because we do not have the global hardware coherent interconnect, the interconnect itself, the cache controller, could be even lower power, so we can afford them to be always on to serve the background tasks. Now, with separate coherence domains, we can have another 20x power saving for this background intelligence. Andrew.
Can you do cache coherence in software more power efficiently than you can do it in hardware?
So I think by doing in software, we can push the complexity in software. We can let the software to define the policy.
Sure.
Yeah.
But is it more power efficient?
It's there's some debate. So this is the debate from like 20 years ago. But I believe you can do it more efficiently in hardware these days. But the thing is that number one, the hardware is not there yet. Number two, we can have more flexible policy in software by doing it in software.
I guess I'm just pushing on the motivation for separate coherence domains is
Right,
power
right.
efficiency.
Right.
And now you're going to put coherence back on top of that. Did we just throw away all the power efficiency?
No, the thing is, basically by implementing the cache coherence in software, we can decide, for example, this domain, this state is not coherent, this state is coherent. Basically, like software-defined memory coherence. Yes.
So it sounds like you just said you want to push more complexity up to the programmer, and they have to think about how data is kept coherent across these coherence domains?
So it's our job to deal with the complexity. By us, I mean a system software designer, not programmers.
Okay. I expect you're going to get to this, but I'm curious to see how this is going to manifest to the programmer in the end, because I expect we can't hide this with layers of system software.
I definitely
And at some
agree.
point, the
Yeah.
programmer's gonna have to do
We should like expose something to the programmers, right? I will talk about that. Okay. So because of the motivation, right? So hopefully across the whole three, we can achieve 1,000 power difference in one mobile device. Now, the design of multiple coherence domains actually is everywhere. It's not some research ideas. It's known in today's mobile devices, from wearables to smartphones to tablets. For example, if we look into iPhone 5s, on the main board of iPhone 5s, we not only have the high power, high performance A7 processor for demanding tasks, browsing, video streaming. We also have the low power processor M7 for background tasks. So they do not have hardware cache coherence, which means they are in separate coherence domains. Now with this architecture, let's define our architectural model more concretely. So we assume there is one mobile device, and there are highly asymmetric cores in this mobile device, hosted by several coherence domains. There is hardware cache coherence within each domain, but not across domains. Multiple cores in different domains can talk to each other by message passing, like hardware message passing at the lowest level, and they can interrupt each other, actually. So with this architecture, the holy grail for software is to span across multiple coherence domains for power efficiency and performance. Let me use one example, email synchronization. So in the email application, in my email application, the background synchronization notification tasks that are running from time to time should be able to run on the low cores in the low power domain. We call it a weak domain. Now the flashy, shiny user interfaces, like email composition, should be able to run on the high power cores. So we can have the best power performance, the best performance, and also the best user experiences. Now these two parts are running in one application, and they do share a lot of state within one application. For example, email contents, conversation thread, search index, and even in-memory database cache. So to realize this scenario, the biggest problem is there is no coherent memory program state supported by hardware. To see why this is a problem, let's look at the good old days to see how software can easily span across multiple cores in one coherent machine. Let's say we have 4 cores in one coherent multi-core machine. This is the case for our laptop, for our desktop, for most of the cloud servers. Each of the core has its own cache. The cache are separated, but kept coherent by the hardware. Let's say we have an OS, can easily span across all cores. The OS could be Linux, Windows, or this legacy OS. So the thread, let's say we have a user thread running on core 0. The thread makes a syscall to create a socket. As part of syscall, it touches some state, which will be cached in core 0's cache here. Later, let's assume the thread has migrated to core 2. It can use the socket S that is created previously, transparently, because the hardware will automatically propagate the cache update from core 0 to core 2. So all this is done in hardware. Neither the user thread nor the OS has to take care of this. This is transparent to them. Everything is simple. Now, in our target architecture, things are different. We have separate coherence domains. The hardware will automatically propagate the cache within one domain, but not across domains. So the inter-domain communication requires explicit software operation, which is way slower than hardware cache coherence, usually by orders of magnitude. So to this end, my work is to enable software stack from application to OS to span across multiple coherence domains. To achieve this goal, I have 3 design objectives. Number 1, we really have to simplify application programming because there are millions of mobile applications up there, and they get used to unified memory view and the one single OS view. And then number 2, we have to simplify OS engineering because mobile OS these days is a huge code base. Android has 1 million lines of code. We cannot build everything from scratch. Number 3, we cannot sacrifice performance. Nobody wants to use a slow system, and under the same level of performance, we want to maximize power efficiency. Now, to achieve the 3 design objectives, I will redesign system software. In redesigning, I will follow 3 design principles. Number 1, because we have asymmetric hardware right now, we should build asymmetric system software. Yes?
So when you're dealing with the disparity in cores and address spaces, you could think about a single OS image with applications spanning it, or multiple OS images with treating them as a little distributed system with breaking apart an application into different services or pieces depending upon the power state. How did you decide to go with a single OS image with a single application and a seamless view versus one that explicitly breaks apart these different domains and asks the programmer to reason about them by building services for each part?
Right. I think from the application program model, you can see later, we still require application programmers to specify this piece of code goes to strong domain, this piece of code goes to weak domain. So that's the only thing they have to do. Basically implement different threads for different domains. But we do provide the unified memory address and one single OS image for them. So that's our approach. Okay, so going back to the principles we follow, number 1, because hardware, we have asymmetric hardware, so we build asymmetric system software. Number 2, we will let software define memory coherence, basically, which means the policy in memory coherence and which state is coherent shared and which state is replicated non-shared. And number 3, we will refactor existing system software rather than building everything from scratch. Now,
I have a question before you go ahead. I'm kind of really new to this. So could you tell what is out there? You said about the Apple A7 and the M5 being present, right? So it's currently there. So what kind of coherence do they implement? Do they implement it in software or is it hardware? Or
right. So right now, I'm going to get that later, but I give you some forecast. Basically, they try to dodge this problem. The Apple just does not allow you as an application program to write any application for the M7. They will provide you some predefined libraries.
And why do they do that?
Because they don't have a good programming model. Yeah. So, okay. So my work has 2 major pieces. Number 1, to enable user programs to span across coherence domains. And then number 2, to span the single OS image. Let's start from span single user program. As we mentioned before, the biggest problem, the biggest challenge to write an application for this architecture is the program state is not coherent, right? As Shoaib mentioned, today's state-of-the-art program framework tries to dodge this problem by only allowing application programmers to write application for the strong processor, for the main processor here.
Don't GPUs let you have effectively 2 coherence domains, 2 kind of incoherent memory spaces, and write whatever you want for both of them?
Right, so there are some research in that actually, but from the hardware, from the lowest abstraction, so they are in separate coherence domains, but there are some research building some soft distributed shared memory to bridge these 2 memory address spaces. Yeah, that's related. Okay. So the state of the art, you only write application for the strong domain, for the most powerful processor, and vendors like Apple, Microsoft will provide the libraries only available for the lowest power core. So at runtime, the 2 pieces of code will talk to each other by message passing. So this approach works, right? But it's very inflexible and actually incurs a lot of development overhead, right?
It's not actually a library. executing it. They provide a library interface that does the message passing, but it must be a service. Right?
Yeah, there's the OS running there, RTOS, like usually. Yeah. So can we do better? We really want to enable one application entirely from the application developer to span across multiple coherence domains. But here, in order to enable this, we have to face the challenge. How do we relieve programmers from dealing with non-coherent program state? So our solution is called Reflex. Reflex is a distributed shared memory. It's one layer below the application. So the idea is kind of intuitive. We will implement the software cache coherence within this layer. Now you may wonder, what's the novelty, right? The distributed shared memory is an old idea from 20 years ago when people are talking about running one application across multiple machines in one cluster. But those classic designs do not serve our purpose well, because one of our major design goals is to enable energy efficiency. So we have to adopt this asymmetric design. We have to keep strong domain, powerful processor, in sleep as much as possible. Now let me give you one minimal example to illustrate how does this asymmetric design work. Let's say we have two coherence domains. One is strong, hosts the powerful processor. One is weak, hosts the low power processor. And both of them share one memory object, which is an array here. So according to our design, any shared memory object is always hosted by the weak domain, which makes it home. Now, if the strong domain wants to access the memory object, it has to send a request to the weak domain. The weak domain will respond, and the memory object will be copied, moved from the home to a requester, from the weak guy to the strong guy. So this is natural. On the other hand, if the weak domain tries to access the memory object here, it cannot send any request. All it can do is to passively wait until the strong domain finishes accessing the memory object and write it back. So the weak domain can go ahead to access the memory object. So this is a minimum example, but hopefully you can get the asymmetric flavor here. Now, the memory model, we build the release consistency, which is very standard. We implement two synchronization primitives, acquire and release. So in propagating memory updates, two domains are asymmetric. Again, the strong domain will eagerly propagate any memory updates to strong domain, to the weak domain. So it can itself, the strong domain itself, can go back to sleep as soon as possible, just to save some energy. The weak domain, on the other hand, will do this lazily. So it will only propagate the memory updates to other guys when it's being asked. So this is try to avoid waking other domains from sleep because of the coherence communication. Now again, this is asymmetric design. This is for power efficiency. Yes, David.
One assumption that you have is you always have an ordering among your domains. So what happens if you have domains that are not clearly ordered, say a GPU and a DSP programmable processor,
right,
where it's not clear which one is the strong and the weak,
right,
for a general purpose program. So do you have a
right? So that's another dimension of the heterogeneity. That's the specializations. I don't have a good answer for that, but I think here we try to address the asymmetric general purpose processors. So we do have a clear order for that. But I think there is one related work to that. They build some software distributed memory between GPU and CPU, and they try to use this similar asymmetric design for that. But in that case, they make the GPU always host the shared memory objects. So the bottom line is, I think the asymmetric, this sort of a principle could apply to that case as well. But we should sort of rethink how to design that system. Okay. So that's about the overall design of Reflex. But we have to implement this, right? We have to build this. So today, as I mentioned, there are many mobile devices have asymmetric multiple coherence domains, multiple processors in one mobile device. But back in 2011, we don't have this flashy, shiny devices back in that time. So we have to build some dangerous prototype ourselves. So what we do is we took a Nokia 900 smartphone from the market, which was nice, shiny smartphone. As many other Nokia smartphones, it has this nice camera, but we have to remove the camera, rip it out in order to access its peripheral bus. So we built a custom board with 2 low-power processor, asymmetric low-power processor on it, and we hook the board with the modified N100 smartphone. And boom, we have one of the earliest prototypes in the world with asymmetric processors, multiple coherence domains. So if we look back today, actually the 2 low-power processors we used before in early days are actually used by people these years, right? So iPhone 5S and Moto X. So they are using the processors we have used before. So something interesting. So based on this hardware prototype, we implement Reflex, and we were able to span one application across 3 different processors, and we can gain 1 order of magnitude higher power efficiency for applications. Yes?
I'm assuming that you're not doing anything to keep those 2 separate things coherent with one another. So there are 3 coherence domains.
Yes,
one
yes.
is the main processor,
Yes, yes.
and then one there, one there.
Yes.
Okay, and those are both kind of like not multi-core processors.
Right, single core. All 3 are single core. So back in that time, we even don't have multi-core for smartphone. So N100 is single core.
I see. Okay. So, all right.
Okay. Okay. So this is about Reflex. To just briefly recap, we built a distributed shared memory in software to provide unified memory address space to application. So application can easily span across multiple coherence domains.
So, go back to the previous slide.
Yeah.
So where is the cache for each of these little processors?
So actually, I don't think they probably have their little L1 cache, but definitely they are not coherent. They have separate caches. Yeah.
So do you manage that cache, or are you oblivious to that?
We can, but they have their separate memory, right? So separate physical memory. So the cache actually does not matter that much. You have to do message passing, explicit message passing between them.
The cache is coherent with respect to the CPU that owns it.
Correct.
It's managing its own cache. Right?
Yeah, sure. That's hardware cache. Yeah. Okay, so that's the first P.
If there's single cores within a domain, what is the definition of coherence?
There is no coherence, right? But we still call it coherence domain, just because we are dealing with multiple cores. Yeah.
Okay.
Yeah.
So each coherence domain doesn't implement any kind of coherence, you just are implementing
We will see multiple coherent cores in coherence domain. So because this is a kind of early system, right? So we will deal with a more complicated system. You will see. Yeah. Yes, Andrew.
So, in terms of more complicated systems, do you know if the current phones that have these different cores, are they using one shared physical memory, or like in the iPhone implementation, do they still have different physical
I will have that. Yeah, sure.
Okay.
Yeah.
I'll show you.
Stay tuned. Okay, so that's about the spanning user program. That's the first piece. Let's talk about the second piece. How do we span one single OS image across multiple coherence domains? So this may be more controversial. You have multiple questions. Number 1, why do we have to span single OS images, right? Can we have can we pin the OS, make the OS only available on one coherence domain? In this case, let's say we make the OS only available on the strong domain. To see why this is a problem, let's use the email example again. See, the email synchronization, a little bit more background. The email synchronization task actually is a battery killer. So this is some research result from Microsoft Research. Every day, when our smartphone is standby mode, the email synchronization task will consume about 14% of battery life in standby mode. So this is a lot of power. It would be nice if when we have asymmetric processors. It would be nice if we can run the email synchronization task in the low power cores here, right? So the strong core can go to sleep, remain in deep sleep mode, so we can save energy. However, with the OS only available on the strong domain, this does not work, because all network activities from the email synchronization task have to go through to the OS, which is on the strong core. Yes?
I don't quite buy that argument, because you could say the same thing about activity recognition 10 years ago. People would say that sensing and processing of data needs to happen within the OS, and guess what? When you distribute the OS to do that, you go to iPhone today and you see a dedicated microprocessor with a library next to it that can actually sense all the sensors, do the processing over there. Why not do something like that for the 10 most power-consuming tasks on the phone? Email syncing being one of those.
Right. So I think the question is, do we need OS support for the background task or not? My personal belief is we definitely need more and more.
There's two questions. Do we need OS support or the other one is do we distribute the OS itself, right? These are two different.
Yes. So email synchronization is one example, right? You definitely want to, for example, create a socket there and use it on the other OS. I will get to that later. And another example is David. They have this prefetching task, which could be running in the background from time to time. So in that case, you really want to have one OS. Right? So I think there are more and more compelling cases to have OS support on low power domains, low power cores. Okay, so basically the idea here is we cannot make the OS only available to the strong domain, because in that case, the background task will wake up the strong domain from time to time, because it has to use the OS services. Now, can we make the OS only available on the weak domain? That does not work either, because the weak domain, low power, also low performance, that will make the OS to be the performance bottleneck of the entire system, which does not work as well. Now, another alternative design is, can we have separate OSs, right? One OS for each domain. For example, OS 1 for the weak domain, OS 2 for the strong domain. This does not work either, because the two OSs have to collaborate to manage many resources in the system. Therefore, we have to modify many things in two OSs, from memory management all the way to many device drivers. This requires a lot of overhead in engineering the OS. So application programming is complicated as well. Like I mentioned before, if you have an application running on OS 2, you create a socket. You cannot reuse that socket on OS 1 because they are separate OS images. So this gives a lot of headache to programmers. Now we are clear. What we really want is one single OS image across multiple coherence domains. But how do we do that? How to design such an OS? So we first have to decide the structure of the OS. One central problem, one central concern to decide the any OS structure is, how is software state shared among OS components? Now, from 1978, this classic paper basically says there are two fundamental OS structures. In today's world, they basically are shared everything and shared nothing. Shared everything is like Windows, Linux. The entire OS is fully coherent, as supported by hardware coherence for most of the time. Shared nothing is you have multiple OS components. They have their own separate memory address spaces, and they will talk to each other by message passing. Now, which of the two OS models, two OS structures fit our purpose well? Neither. So to motivate our decision, let's see one key observation we have. If we look into today's mobile OS, mobile kernels, for example, Linux, we can roughly categorize all OS components, or we call it services, into a few sets. One set is core services. Basically, they are like the small infrastructure of the whole OS, performance critical, developed by a small number of people, like virtual memory, page allocation, scheduling, etc. On top of core services, there is a large set of extended services, like device drivers, network, file systems. So they are large in number, and they are developed by a lot of people, Microsoft, Google, Samsung. Actually, there is an ecosystem behind them. So compared to core services, they are less performance critical. Now, with this observation, we propose our OS model. We call it shared most OS model. So basically, the core services, small set, performance critical, are replicated as shared nothing instances. So one instance for each coherence domain. On top of core services, the large number of extended services can be transparently shared across coherence domains. So their source code could be reused. If we try to plot our OS model into the spectrum of OS structure, you can see we are somewhere in the middle, like here. This is because we're trying to find a balance point between the ease of engineering and programming versus the performance and power efficiency. Now, with the OS model, let's build the OS. But before that, let me introduce one important hardware background. So we have been talking about multiple coherence domains in one mobile system, but in real world, there are two major ways to integrate them in one mobile system. So number one is coherence domains on separate chips, like people mentioned previously. So in this case, each chip, each coherence domain have their separate memory and I/O. And as multiple chips are connected through some relatively low speed, high latency peripheral bus, like I2C, SPI. That's a case for example, our Reflex prototype, we have 3 different chips. And also for iPhone 5s, 2 separate chips. So that's the first type of integration. The second type is coherence domains, multiple coherence domains on one single chip. For example, in this case, there are 2 coherence domains on one same chip. Most likely, they share the same set of physical memory and I/O. I will give concrete example for that later. To add one more twist to this big picture, sometimes these 2 types of integration can coexist in one mobile system. For example, in this case, this chip can have multiple coherence domains inside it. Now, let's look at the 2 types of integrations again. Coherence domains on separate chips and on same chip. Now, with this background, let's try to implement our own OS. Because Reflex was targeted on multiple chip case, it was natural for us to try to build the OS across multiple chips, like this. But back in that time, we found this problem to be really difficult because the physical memory are separated, right? And the interconnect is relatively slow. So we do have a lot of concerns back in that time. For example, how do we ensure the performance of the OS? Because OS is such a performance-critical piece. And number 2, should we build everything from scratch? What kind of components can we reuse? And number 3, do we have enough architectural support to build such an OS? Back in that time, we did not have good answers for this design questions. So let's take one little step back. Let's try to build the OS for a little bit different architecture, which is the second type of integration, where cores are slightly tightly coupled in one chip. So the advantage is that we do have shared physical memory, and the interconnect is faster because the interconnect is on chip. So these are good news for OS designers like us. So we will build the OS for this architecture first. So the hardware platform we chose is TI-OMAP4. This is a popular mobile system on chip, has been used in many popular mobile devices, from wearables to smartphones to tablets. On the chip of TI-OMAP4, there are 2 coherence domains. One coherence domain hosts different type of cores. So for example, we have A9 core in one coherence domain, which is for powerful, demanding tasks. And we have M3 core for the weak domain, which is for background tasks. They do not have global hardware cache coherence, and they can share the same set of I/O and physical memory. They talk to each other, different cores in different domains, talk to each other by hardware message passing. So this is hardware support. They can pass around 32-bit messages, so very short messages. And therefore, they can interrupt each other. Now, by applying our shared most OS model to this hardware architecture, we built our experimental OS. We call it K2, which is a mobile OS spanning heterogeneous coherence domains. So K2, inside K2, on top of 2 coherence domains, we have 2 kernels, 1 kernel for each coherence domain. Inside each kernel, like we said before, core services are replicated, 1 instance for each coherence domain. On top of core services, there is a layer of OS-level distribution memory which present the illusion to all extended services, as if they are running on a fully coherent machine. So we can reuse the source code from all those extended services. So let's talk about the software distribution memory here. The idea here actually is very close to what we have used for Reflex. Basically try to provide this illusion to higher level software. But the implementation here is different because we have hardware MMU, and with the hardware support, the latency, the performance of distribution memory actually is way better. For each access miss, we have about 15 microsec. I will talk about how does the 15 microsec impact the overall performance. Now, core services, there are, like we have mentioned before, there are multiple core services, and each core service is replicated as separate instances. Now, how to coordinate those instances is case by case. For example, let's say page allocator. This is one important core service. multiple independent instances of page allocators will collaborate with each other to manage the same set of physical memory. K2 will coordinate those instances by inserting balloon drivers into multiple kernels, like this. So you can imagine balloon drivers, they're just like dummy device drivers. Controlled by K2, their job is actually very simple. A balloon driver can inflate. Basically, the K2 will try to get a large page block from the local page allocator. It can also deflate. Basically, the K2 will put the large page block back to the page allocator. Now, with multiple balloon device drivers, K2 can move large page blocks around different page allocators. So it can control how much memory is available to each of the kernel, to each of the each instance of the page allocator. This design has two benefits. Number one, the balloon here, this one is almost transparent to page allocator. So we do not have to modify the page allocator, the Linux page allocator source code too much. So we still can reuse most of the Linux page allocator source. And number two, because we are moving around the large page blocks, so we actually can reduce the inter-domain communication for good performance. So that's about the page allocator. Let's look back at the structure of K2 to recap. Basically, core services are replicated as shared nothing instances, and K2 will manually explicitly coordinate them. There is a software distributed shared memory which will present one illusion to all external services. So their source code could be shared.
Quick question. The other core services were generally easier or harder to implement in this way?
There are, for example, scheduler, and also the interrupt management. So each core service is case by case. Actually, I will say it's challenging. But the good news is that there is a small set of core services. So that's fine.
How many?
Like right now it's 5 or 6, something like that. Yeah. How much time do I have? 15 minutes, OK. So I will skip this hacking part. So this is basically some little hacking fun we have. So imagine, just to like briefly summarize, we have two kernels in different instruction sets. So they have different ISAs, two binaries. But the thing is, two kernels will share the function pointers at runtime. So the problem is if one kernel tries to follow the function pointer pointing to the wrong instruction set, it will crash. And it's sort of an unrecoverable crash. So how do we do that? How do we handle the function pointer with a little bit of compiler support and runtime support? So this is some hacking fun we have during the kernel implementation. So I will quickly skip that. Let's look at the evaluation. So how well does K2 work? So we try to answer 3 questions in the evaluation. Number one, how much energy efficiency can we get? So we compare with Linux. Because K2, our OS, can span across multiple asymmetric processors, we can actually exploit the low power processor for high energy efficiency. Not surprisingly, we have much higher energy efficiency, like up to 10x. This is good, amazing, but as we planned.
Measured by what? You have a workload, a benchmark?
Yes, we have 3 typical light OS benchmarks. So typical 3 like OS workloads. And we actually measure power consumption by hooking wires to the power rails on the dev board.
So is there anything specific about those benchmarks?
So this is like 3 like typical OS benchmarks, OS used by many applications. For example, the DMA is like used by almost every device drivers, and the file systems, of course, like commonly used. Demetrius.
So would you get the power savings in the UDP loopback, right? Because I would assume that in this case, the processor is on, the radio is on, the display is on, so you should have a huge static overhead, right? And if you're doing UDP, I would assume that the only way to control the 4G radio, right, would be through the high-end processor.
So the display is off, actually, in this case. We're talking about the background tasks, like the email synchronization in the background, and also prefetch in the background. Actually, display is off.
So if I were to give you a baseline, the iPhone 5S that has the M7 processor, how would your power numbers compare to the implementation of the IS?
Right. So iPhone 5s cannot run the OS service on that low power processor at all. So you have to use a strong processor, the high power one, for any OS services you have. So you have to wake up the strong processor from time to time.
So, trying to understand, the black bar and the green bar are the two different processors. You're comparing the main processor to the...
So the black bar actually, this is energy efficiency. So the y-axis is the energy efficiency. So basically we use basically write some user space driver to stress the OS service, the same OS service.
Where, on what core is it running?
What core is the brown and the green running?
Okay, so on Linux, the OS service is always running on the strong core.
Okay. So for UDP loopback, that's essentially just a local computation exercise. And you're just showing that the main core uses a lot more energy than...
Right.
Okay.
So your baseline is basically everything runs on the big core.
Yes.
Nothing. You're not using the small one.
Right. Because basically, the one of the top goal of K2 is to enable OS services running on the small one, right? So we can exploit. We can open the small processor to a lot of OS services.
And so those three workloads, just to clarify, those three workloads are all things that can run on the small core with K2.
Yeah, of course.
Do you have any examples of workloads that can't run on the small core?
So there are, for example, some hardware. By design, some hardware feature is private to the big core. For example, the interrupt. So if the interrupt is the hardware interrupt only goes to the big core, so then you cannot run it on a small core. But that's a hardware limitation. Yes, Alec.
So for the UDP loopback experiment, I just want to see if I understand. There's not an actual, there's no actual radio involved in this experiment.
No.
If you did have a radio involved in that experiment, at that point then the actual throughput would start to play a factor, and you might actually have to keep the radio on longer if you were using the less powerful core.
Yeah.
That might offset a lot of those benefits.
Yes. So I think there are two effects if we have real radio. The idle time will be longer between two packets. That will penalize the big core, because the big core idle is more power hungry. But I agree with you, definitely there is a large number of the radio power consumption. Yes, Dimitri. Okay.
One last thing is about timing, right? How is the timing of the DMA of the UDP or the EXT is affected by the fact that you're running on rolling also?
Right. I think so we actually try different sizes of the work. For example, we try different sizes of DMA, like 4K, 128K, and 1 megabyte. When it's more I/O intensive, our K2 will do better because the idle time between the I/O operations actually are very power hungry for the big core. Because the small core can idle with much lower energy of power.
I guess this is also assuming that the bottleneck is the actual I/O of the memory rather than anything else. So the processor is much faster than the speed of the memory.
Right. So actually, that's one of the dimension. The other thing is for the OS workloads. If we look at the energy per instruction, this kind of energy efficiency metric, in that case, the small core can be more power efficient than the big core because the OS workloads are kind of irregular. It can hardly benefit from the advanced microarchitecture features like deep pipeline, branch prediction, something like that, which is featured by the strong core. Yeah, G.
So I'll just maybe follow up on Dimitri's previous question.
Yeah.
Which is, just take the other extreme that you hard code everything on the small core as a library or the small OS.
Yeah.
And use those to support these benchmarks.
Okay.
Do you have a sense of where are you in that spectrum? Are you much, is there still a lot of space to improve? Right? Does the flexibility cost you anything or not?
Yeah, so I think in terms of energy efficiency, there is no difference because if you can handcraft the OS, it's the same, right? But the thing is that development overhead is much higher. You have to craft the two separate OS images. Application is difficult to write because the application developer has to deal with two OSs.
So you believe you're as efficient as handcrafted
Yes.
two different OS?
Yes. Yeah. So remember, we have three goals. Number 2 is to simplify OS engineering. So this is to achieve that goal. Okay, so this is about K2, but let's try to jump out. Look at the big picture again. K2 actually spans one single OS image across different coherence domains in one chip. On one chip. Remember, we have this goal before. We tried to build the OS for multiple chips. Back in that time, we felt this was difficult because performance concern, OS engineering concern, and also architectural features concern. We feel that was difficult. With insights and knowledge from K2, we feel this was actually this is viable. It's durable. So for performance concern, we should still use the shared most OS model. But in this case, because cores are more loosely coupled, so more state should be replicated instead of shared coherent. For OS engineering, to control the OS engineering, to reduce the overhead, the engineering overhead, we should still do refactoring, basically reuse OS components from the legacy code base. And architectural features, we really need hardware MMUs for different chips, so we can build the one unified memory address space easily. And we really need the hardware messages, efficient hardware messages across different chips, so we can do inter-kernel communication more efficiently. So that's something we are trying to do right now. This is ongoing work. Now, I will skip related work. So to recap the things that has been done, the target architecture is highly asymmetric processors in one mobile system. And there is no global hardware cache coherence among them. So in order to span the OS, the entire software stack across those processors, we have redesigned system software to achieve two important views. One is coherent memory view, so application can span across coherence domains. The other one is single OS view, so application can still see one single OS. So we have followed three design principles, which we believe will be useful for future system design. Number one is we build asymmetric system software. Number two, we let software to define the policy in memory coherence. Number three, we refactor existing code base, system software code base, rather than rebuilding everything from scratch. So that's the work has been done. Let me quickly talk about the future directions, just to be on time. So what I have done is system software for non-coherent, asymmetric, general-purpose processors. Looking into future, I try to address systems challenge from three directions. Number one is higher heterogeneity. Number two, higher parallelism. These two are for mobile devices, for wearable mobile devices. And to look beyond mobile device into larger systems. Let's talk about higher heterogeneity. So these days, we not only have general purpose processors in one system, asymmetric general purpose in one system, we also have, for example, the computational geography, the DSP, multimedia core, sensor core in one mobile system. Now, how do we build system software? How do we build system support for them? So this is still an open question. Because some of the cores may be able to run the OS code, some of them maybe not. Some of them may be able to run the program code, some of them maybe not. But I think there are four aspects we should address as a system software designer. Number one is abstraction. We should provide good abstraction for application developers to write an application for all this heterogeneous hardware. Multiplexing. We should enable multiple programs to fairly share the same set of heterogeneous hardware. Protection. If we want to run some user code on one of the heterogeneous processor, we do not want to mess up other state in the system. And the configuration. The dependency among the large type of cores that are like sort of subtle. By dependencies, I mean functionality dependency, power dependency, voltage dependency, like clock dependency. How do we provide system support to simplify the procedure, and how do we like automatically verify this process, this configuration? So that's a big question. Now, higher parallelism. So we not only have more types of cores, we also have larger number of cores. So in a few years, we are going to have tens of CPU cores and a few hundreds of GPU cores, all in one mobile system. How do we use the extra number of cores for higher interactivity? This is an old question, actually, from 20 years ago. In 2010, people ask, how many cores do we need for one interactive system? They say, you need 2 cores. Now, since that, 10 years has passed, people ask this question again. Because no problem. Yeah. Let's see.
Are you running K2 on that laptop?
I wish I could. Yeah. Okay, let's play it. Try to restart. Okay. So basically, 10 years has passed since 2000. There are many, many new like feature-rich interactive applications. So people ask this question again: how many cores do we need for an interactive system? They say you need one more core, right? But today, the extra number of cores is an asset. We have to use them, or we will waste them. So there is an open question: how do we can we have a novel use of many cores for interactivity? For example, can we use extra cores to support natural user interface and augmented reality? This sort of a new interface. And can we parallelize interactive workloads, for example, HTML5? So I'm looking forward to working with programming language people and algorithm people on this direction. And some even crazier idea is, can we use extra cores to speculate user inputs, to compute all the possible outputs, have them ready before the system sees actual user input? So this can probably give us the like 1 millisecond latency. So that's even crazier idea I will try to explore. Now, look beyond the mobile system. I will try to quickly wrap up. To look beyond mobile system, heterogeneity is everywhere in larger system. For example, GPU, CPU, this is probably the most successful heterogeneous system in the last 10 years. And if we look at the edge of the cloud, there is something called the cloud base station, which is highly heterogeneous as well. We can see them as regional data centers. For example, the TI Keystone SoC is a heterogeneous SoC for server market. So inside one Keystone SoC, there are a bunch of ARM processor, general purpose ARM processor, and a bunch of DSP, so that we can run the general purpose workloads and the communication workloads, 3G, 4G, side by side. In a real system, in a real server, there are a lot of Keystone SoC interconnected. For example, this is the case for HP Moonshot server. In a cloud-based station, in a regional data center, there are hundreds of servers like that. How do we program the highly heterogeneous system? And how do we debug such a highly heterogeneous system? So these are open questions. Now, if we look at the very tip of the cloud, this is basically the base station, the cellular tower our smartphone direct talks to. They are heterogeneous as well. This is something we have built, Clay has built actually at Rice. So the idea is, basically the spectrum is really expensive. It's a premium in today's wireless communication. In order to improve the utilization for spectrum, we can use multiple antennas and use a lot of number of heterogeneous computer resources. So we can improve the utilization for heterogeneous for the spectrum. So on this direction, I'm looking forward to working with wireless communication people to address the system software challenge here. Now, finally, let me try to position myself in the computer stack. So I'm working on the low-level system software, which is on the boundary between the hardware and the software. So I try to co-design the system software by working closely with the architecture and hardware people. And I'm trying to look into the hardware itself, look for this cool architecture support for system software. I will co-design the system software with folks from other areas like compiler, programming language, networking, and distributed systems. And with the co-design system software, hopefully we can provide good, strong support for all these high-level applications. For example, algorithm, human-computer interaction, machine learning. And we can provide a strong guarantee for high-level concerns like security and privacy. So to recap the whole talk, what I've done is to redesign system software for non-coherent asymmetric processors. So one software stack can transparently span across multiple coherence domains. Looking to the future, I'm ready to address systems challenges from 3 directions: higher heterogeneity, higher parallelism, and larger systems. Thank you. Yes?
Yeah, so I had a question about application programmability.
Yeah.
It seems like in mobile, you want it to be easy to make programs for these kinds of devices, whether they're heterogeneous or not. And I like the idea of using shared memory because that's a familiar interface that people are comfortable with. I think one of the downsides of shared memory is that the cost of communication between different parts of the system is implicit. When you have hardware support for coherence, I think people are willing to tolerate that implicit cost and kind of maybe unpredictable performance because you have hardware support and the costs aren't that high. But now you're kind of proposing that instead of hardware coherence, we use software coherence to do the same kind of thing. And it seems like the performance predictability is going to, the performance is going to be much less predictable because now the costs will be higher when communication actually happens through that implicit mechanism. So I guess the question here is, did you look at the trade-offs in using what you've described versus using something that makes the performance difference explicit if you have operations that are going to be doing communication or not doing communication because the performance cost is higher when you use the software?
Exactly. I think that's a good point. So right now, the program model we propose, user program model we propose is user implement different threads for different coherence domains because the fundamental reason is migration is hard, right? Migration is hard from one domain to another domain. This also makes the performance boundary explicit. So they know this thread is running on the high power domain, this thread is running on the low power domain. And they know the sort of the sharing between the two threads actually across domains. But whether this is ideal, I don't know. But the thing is, I think it definitely makes sense to provide some sort of a hints, like bidirectional hints from the system to the application and also from the application to the system. Yeah, but the one good news we have is the contention between these two parts is not that high in mobile, in the background tasks we targeted, right? Because they don't communication like all the time. So that sort of relieve the problem.
It's just a follow-up question, given that that's how you guys address that problem is, how easy is it for an application programmer to identify what should go on the weak and what should go on the strong? Because I think if you just looked at a program without understanding what it does, it might be difficult to parcel it out.
Yeah, so basically, right now in next application, the boundary is implicit. But I believe it's kind of doable for application programmer to specify the performance need, right? But not the power need. But as long as they specify the performance need, I think we can do that kind of a partition. They only have to, my philosophy is that programmers only have to reason about the performance, not about the power consumption. But that's just me. Yeah. Okay.
Okay, thank you.
Thank you.